Preparing for a semiconductor packaging engineering interview? You've reached Interview Guide, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Can you explain the role of semiconductor packaging in overall device performance and reliability? Packaging is the bridge between the silicon die and the real system. I look at it as electrical routing, thermal management, mechanical protection, and environmental shielding in one solution. A good package reduces parasitics, removes heat efficiently, protects fragile die and interconnects, and supports high-volume assembly. The package choice can directly impact speed, power integrity, yield, reliability, and cost. So I treat packaging as a product-level design decision, not just an assembly step. While answering, focus on electrical interconnect, mechanical protection, thermal dissipation, environmental isolation, form factor, manufacturability, and how package choices affect signal integrity, power delivery, cost, and field reliability. Question 2. What are the key differences between wire bonding and flip chip packaging? Wire bonding connects die pads to package leads using gold, copper, or aluminum wires, usually from the die edge. It is mature, flexible, and cost-effective, but has higher inductance and limited I/O density. Flip chip uses solder bumps or copper pillars to connect the die face down to the substrate. That gives shorter interconnects, better electrical performance, higher I/O count, and improved thermal spreading, but it needs tighter process control, underfill, and more expensive substrates. Make sure to cover interconnect geometry, electrical parasitics, I/O density, thermal path, assembly complexity, cost, substrate requirements, and typical applications where wire bond or flip chip is preferred. Question 3. How would you approach thermal design for a high-power semiconductor package? I start by defining the power map, maximum junction temperature, ambient condition, and allowable thermal resistance. Then I identify the dominant heat path, die to attach, substrate or lead frame, lid, TIM, and system heatsink. For high power, I would evaluate high conductivity die attach, exposed pads, copper clips, heat spreaders, or lid materials. I use simulation early, then validate with thermocouples, IR imaging, or T3-stir. The best solution balances thermal margin, cost, stress, and manufacturability. In your answer, talk about junction to case resistance, heat flow path, die attach materials, heat spreaders, thermal interface materials, simulation, power maps, package constraints, and validation through thermal testing. Question 4. What causes package warpage and how do you control it during manufacturing? Warpage mainly comes from CTE mismatch and residual stress across the package stack. During molding, curing, and reflow, materials expand and shrink differently, so the package bends. I control it by balancing the stack up, optimizing substrate and mold compound properties, adjusting die thickness, controlling cure and reflow profiles, and using warpage simulation before build. In production, shadow moire or laser metrology helps track trends. Excess warpage matters because it drives solder joint opens, assembly defects, and reliability failures. Be sure to mention coefficient of thermal expansion mismatch, material stack asymmetry, cure shrinkage, mold compound properties, substrate thickness, reflow temperature profile, simulation, metrology, and design process mitigation methods. Question 5. Why is underfill used in flip chip packages, and what properties matter most? Underfill protects solder bumps from thermomechanical fatigue. In flip chip, the silicon die and organic substrate expand differently during temperature cycling, so the bumps see high strain. Underfill distributes that stress over a larger area and improves drop and thermal cycling reliability. I care about viscosity for flow, low voiding, strong adhesion, compatible CTE and modulus, TG, cure behavior, and moisture performance. The trade-off is that underfill improves reliability, but can complicate rework and introduce stress if poorly selected. While answering, cover stress redistribution, solder bump fatigue, capillary versus molded underfill, viscosity, CTE, modulus, glass transition temperature, adhesion, voiding, cure profile, and reliability performance. Question 6. How do you qualify a new semiconductor package for production release? I qualify a package by first defining its use conditions, failure mechanisms, and applicable standards, usually JEDEC-based. A typical plan includes preconditioning, temperature cycling, HAST or unbiased HAST, high temperature storage, HTOL if device-level stress is needed, board-level drop or bend for mobile products, and solderability checks. I also include electrical test before, during, and after stress, plus failure analysis on any rejects. Qualification is not just passing a checklist. It confirms the design has margin for the intended application. Make sure to discuss qualification planning, JEDEC standards, preconditioning, temperature cycling, HAST, HTOL, mechanical tests, sample size, failure criteria, electrical readouts, construction analysis, and risk-based decision-making. Question 7. Describe the typical process flow for assembling a molded lead frame package. For a molded lead frame package, the flow usually starts with wafer backgrind and dicing, then die pick and attach onto the lead frame using epoxy, solder, or film. After die attach cure, wire bonding creates electrical connections. The strip is then molded, followed by post-mold cure if required. Next come plating or lead finish steps, trim and form, singulation, inspection, marking, and final test. Critical controls include die attach voids, bond pull strength, mold flash, coplanarity, and moisture sensitivity. In your answer, mention wafer saw, die attach, cure, wire bond, mold encapsulation, post-mold cure, plating or lead finish, trim and form, singulation, inspection, test, and common controls. Question 8. What are common die attach materials and how do you choose between them? Die attach selection depends on thermal, electrical, mechanical, and process requirements. Epoxy is common and cost-effective, with electrically conductive or insulating options. Solder gives good thermal and electrical performance, but needs metallization compatibility and reflow control. Sintered silver is excellent for high power and high temperature applications, but it is more expensive and process sensitive. Die attach film helps with thin die and uniform bond lines. I choose based on power dissipation, stress tolerance, void limits, package type, throughput, and reliability targets. Be sure to cover epoxy, solder, sintered silver, die attach film, thermal and electrical conductivity, bond line thickness, voiding, cure or reflow temperature, stress, cost, and application needs. Question 9. How would you investigate a wire bond lift failure found after reliability testing? I would first confirm whether the lift occurred at the ball, wedge, pad, or lead finger, because each points to a different root cause. Then I would review bond pull data, process logs, plasma cleaning, capillary condition, bond force, ultrasonic power, and temperature. Failure analysis would include optical inspection, SEM, EDX for contamination, and cross-sectioning to assess intermetallics or pad damage. Corrective action might involve cleaning improvement, bond parameter optimization, metallization review, or material change. While answering, focus on isolating failure timing, visual inspection, bond pull and shear data, intermetallic formation, contamination, pad metallurgy, plasma cleaning, bond parameters, cross-sectioning, and corrective actions. Question 10. What is moisture sensitivity level, and why is it important for package assembly? MSL defines how sensitive a package is to absorbed moisture before board-level reflow. If moisture is trapped inside the package, rapid heating during reflow can create vapor pressure, causing delamination, cracking, or the classic popcorn effect. JEDEC preconditioning classifies the floor life and handling limits. In production, we control this through dry packing, humidity indicators, floor life tracking, and baking when needed. CSAM is often used to detect delamination after stress. Good MSL control prevents assembly-induced reliability failures. Make sure to explain MSL classification, moisture absorption, popcorn cracking, delamination, floor life, bake requirements, dry packing, reflow exposure, acoustic microscopy, and JEDEC handling guidelines. Question 11. How do you evaluate solder joint reliability for a BGA package? BGA solder joint reliability depends on package geometry, ball alloy, pad design, board material, and use environment. I usually evaluate it with temperature cycling for fatigue and, when relevant, drop or bend testing for mechanical shock. Simulation helps identify high-strain corner balls and assess the effect of standoff, package size, and CTE mismatch. After testing, die and pry, cross-sectioning, and SEM confirm crack location. The goal is not only lifetime prediction, but also design feedback for pad, ball, and stack-up optimization. In your answer, cover solder alloy, ball size, pitch, pad design, standoff height, board stack-up, thermal cycling, drop testing, strain distribution, finite element analysis, and failure analysis. Question 12. What is delamination in semiconductor packages, and how can it be prevented? Delamination is separation at an internal package interface, such as mold compound to die, lead frame, substrate, or die attach. It often comes from poor adhesion, contamination, moisture absorption, cure issues, or thermomechanical stress. Prevention starts with clean surfaces, compatible materials, plasma treatment when needed, proper cure profiles, and robust moisture control. Design also matters. Sharp corners, large stress gradients, and weak interfaces increase risk. CSAM is my preferred non-destructive screen because it quickly shows delamination location and growth after reliability stress. Be sure to discuss interface adhesion loss, moisture, contamination, cure conditions, mold compound compatibility, plasma treatment, surface roughness, CTE stress, CSAM detection, and design process prevention strategies. Question 13. How would you improve yield in a packaging assembly line with increasing reject rates? I would start with a Pareto of reject modes and segment the data by lot, tool, operator, material batch, shift, and process step. Then I would inspect trend charts to see whether the issue is sudden or drifting. For the top defect, I would use targeted failure analysis and process audits rather than guessing. A DOE may be useful if multiple variables interact. I would also contain suspect material, verify the fix statistically, and update control plans so the yield gain stays permanent. While answering, cover data segmentation, Pareto analysis, process mapping, lot and tool correlation, metrology, control charts, DOE, failure analysis, containment, root cause verification, and sustainable corrective actions. Question 14. What are the main challenges in fan-out wafer-level packaging? Fan-out wafer-level packaging removes the need for a traditional substrate by embedding die in mold compound and building redistribution layers over it. The big challenges are die placement accuracy, die shift during molding, wafer warpage, RDL line space control, and yield loss because multiple die and process layers are combined. Known good die handling is critical. Fan-out is attractive for thin form factor, high I/O density, and good electrical performance, but process control and cost modeling must be very disciplined. Make sure to mention die shift, wafer warpage, redistribution layer routing, fine line lithography, molding, known good die, yield loss, thermal management, panel scaling, and cost performance trade-offs. Question 15. How do package parasitics affect high-speed device performance? At high speed, the package becomes part of the electrical circuit, not just a container. Bond wires, bumps, traces, vias, and planes add resistance, inductance, and capacitance that can cause ringing, delay, crosstalk, ground bounce, and power rail noise. I manage this with short interconnects, controlled impedance, solid return paths, decoupling strategy, and package extraction models. S-parameters or IBIS models help correlate simulation to measurements. Flip chip generally beats wire bond when parasitics and I/O density dominate. In your answer, talk about inductance, capacitance, resistance, signal integrity, power integrity, ground bounce, impedance control, return paths, package modeling, S-parameters, and layout-driven mitigation techniques. Question 16. What reliability tests would you recommend for an automotive-grade semiconductor package? For automotive, I would build the plan around AEC question number 100 or question number 101, depending on device type, and the product mission profile. Core tests include temperature cycling, HTOL, high temperature storage, HAST or biased HAST, and preconditioning. For power packages, I would add power cycling, because junction temperature swings drive fatigue. Mechanical shock, vibration, and board-level reliability may also be required. Automotive qualification is stricter, because lifetime traceability and low defectivity matter as much as passing initial reliability tests. Be sure to cover AEC question number 100 or question number 101 expectations, temperature cycling, HTOL, HAST, high temperature storage, power cycling, mechanical shock, vibration, solder joint reliability, traceability, and zero defect mindset. Question 17. How do you select substrate materials for an advanced package? I select substrate material by matching electrical, thermal, mechanical, and manufacturing needs. For high-speed applications, dielectric constant and loss tangent are important. For large flip chip die, CTE and stiffness affect bump fatigue and warpage. For high power, thermal conductivity and copper design matter. Routing density drives layer count, via type, and line space capability. Ceramic substrates provide thermal and dimensional stability, while organic substrates usually win on cost and ecosystem. The best substrate is the one that meets performance without overbuilding cost. While answering, focus on organic versus ceramic substrates. CTE, dielectric constant, loss tangent, routing density, via technology, thermal conductivity, mechanical stiffness, cost, supplier capability, and reliability constraints. Question 18. What are chiplet and 2.5D packaging, and what engineering issues do they introduce? Chiplet packaging integrates multiple smaller dies into one package, often using a silicon interposer, organic interposer, or bridge technology in 2.5D architectures. It solves scaling, yield, and heterogeneous integration problems by mixing logic, memory, analog, or RF dies. The new challenges are interconnect density, power delivery, thermal coupling between dies, warpage, assembly yield, and test coverage before final integration. Known good die strategy becomes essential. Successful chiplet products require package, silicon, test, and system teams to co-design from the start. Make sure to discuss heterogeneous integration, interposers, silicon bridges, high bandwidth interconnects, thermal coupling, power delivery, warpage, assembly yield, known good die, test strategy, and system-level co-design. Question 19. How would you perform failure analysis on a package that fails after temperature cycling? I would first reproduce and characterize the failure electrically to know whether it is open, short, leakage, or parametric drift. Then I would use non-destructive methods such as X-ray for solder or wire issues, and CSAM for delamination. Based on the signature, I would cross-section, die and pry, or decapsulate. SEM and EDX help confirm cracks, corrosion, or contamination. Temperature cycling often points to CTE-driven fatigue, but I would only call root cause after connecting physical evidence to the stress history. In your answer, cover failure confirmation, electrical signature, non-destructive inspection, CSAM, X-ray, cross-sectioning, die and pry, SEM, fracture surface analysis, material history, and linking evidence to mechanism. Question 20. How do you balance cost, performance, and reliability when choosing a package architecture? I start with the product requirements: I/O count, speed, power, size, environment, lifetime, and volume. Then I compare architectures such as QFN, BGA, flip chip, fan-out, or 2.5D against those needs. The cheapest package may fail thermally or electrically, while the most advanced option may add unnecessary cost and supply risk. I look at mature supplier capability, yield learning, qualification effort, and roadmap flexibility. A strong recommendation explains the trade-offs clearly and leaves margin where failure would be expensive. Be sure to mention product requirements, volume, application environment, electrical and thermal targets, manufacturability, supply chain maturity, qualification burden, risk assessment, total cost of ownership, and roadmap flexibility. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.